Welcome back to the channel, and happy holidays. Hope you're enjoying some well-deserved time off, and if you're spending part of it nerding out on AI infrastructure, you're in the right place. Today, we're exploring why AI training at scale requires completely different infrastructure than traditional cloud computing. The answer comes down to two words: bare metal. If you're into these kinds of deep dives, hit subscribe and share with anyone curious about AI infrastructure. Here's what we'll cover: why virtualization creates a hidden performance tax on GPU workloads, how technologies like GPUDirect and RDMA enable direct memory access that hypervisors block, and how Kubernetes can orchestrate bare metal resources without sacrificing cloud-native automation. This is the infrastructure behind every major LLM breakthrough. Let's get into it. Let's start with a reality check. When GPUs operate through a hypervisor layer, AI training suffers a 15 to 25% real-world performance penalty. This is called the virtualization tax. You might have seen benchmarks claiming only 4 to 5% overhead, but those are controlled tests. Production workloads tell a different story. There are three main culprits. First, VM exits constantly interrupt the GPU compute flow whenever privileged instructions execute. Second, memory address translation adds latency at every single data access. Third, noisy neighbor effects cause unpredictable performance jitter that compounds over time. Here's why this matters. AI training runs at near 100% GPU utilization for days, sometimes weeks. A 20% slowdown doesn't just mean 20% longer training. For large models, it means weeks of additional compute time. But there's a deeper problem. AI training isn't compute-bound, it's memory bandwidth-bound. This is called the memory wall. From 2016 to 2022, GPU compute power increased 46 times, but memory capacity only grew 5 times. That gap is widening. Here's the scale. Generating 1,000 tokens per second for a 70 billion parameter model requires 140 terabytes per second of memory bandwidth. And tensor parallelism alone generates over 75% of all data transferred between GPUs during distributed training. A single query to Llama 3.1 70 billion requires 20 gigabytes of synchronization data per GPU. This is why virtualization overhead is so devastating. Any additional latency directly slows training. Memory now consists of over 50% of AI server costs. It's the critical bottleneck. So how do we move data fast enough to keep GPUs fed? The answer is GPUDirect RDMA. It allows network adapters to read and write directly to GPU memory, completely bypassing the CPU. The gains are dramatic: 2 to 8 times more bandwidth with significantly lower latency. Within servers, NVLink provides 900 gigabytes per second between GPUs. Across servers, InfiniBand delivers 400 gigabits per second with sub-microsecond latency. But here's the critical point. This only works with direct PCIe paths. When you add a hypervisor, the IOMMU can redirect PCIe traffic through the CPU. This doesn't just slow things down, it can cause the system to hang entirely. GPUDirect requires direct memory mappings that virtualization layers simply can't provide without complex configuration. Now, this matters far more for training than inference. Training runs continuously for weeks at near 100% utilization. Every percentage point of overhead compounds over millions of iterations. Inference handles individual requests where a few extra milliseconds is often acceptable. Training also requires constant GPU to GPU synchronization. Gradients flow between thousands of accelerators every iteration. Any bottleneck stalls the entire cluster. This is why hyperscalers use virtualized infrastructure for inference, but insist on bare metal for frontier model training. Let's look at how GPUs actually communicate during training. NVIDIA NCCL, the collective communications library, orchestrates all GPU to GPU data movement. The most critical operation is all reduce. After every iteration, each GPU computes gradients for its data portion. All reduce combines these across all GPUs so every accelerator gets the same updated weights. Nickel is smart about topology. It uses NVLink within servers and GPUDirect RDMA over InfiniBand across servers. But when virtualization blocks these direct paths, Nickel falls back to slower CPU-staged transfers. That's where the performance penalty hits hardest. Now, if we remove the hypervisor, how do we get cloud-like automation? The answer is Kubernetes on bare metal. You get direct hardware access combined with container orchestration. No hypervisor, no VMs, just containers running directly on hardware scheduled by Kubernetes. Compare the paths. Virtualized, application to container to Kubernetes to VM to hypervisor, then hardware. Bare metal, application to container to Kubernetes directly to hardware. The NVIDIA GPU operator automates driver deployment. SRIOV enables direct network access, bypassing software switching. Organizations report up to 30% performance improvement after migrating to bare metal Kubernetes. You get cloud automation with HPC performance. Let me give you a concrete example. CoreWeave. CoreWeave runs CKS, their Kubernetes service, directly on bare metal GPU nodes. No hypervisor, no VM layer, zero virtualization overhead. Every server includes a Bluefield DPU for network isolation. The infrastructure is purpose-built for AI. Their mission control platform provides topology-aware scheduling. It knows which GPUs share NVLink, which nodes have the fastest InfiniBand paths, and places workloads accordingly. This architecture enables their MLPerf records, 2 times faster than comparable clusters. We'll do a dedicated deep dive on CoreWeave in a future video. Make sure you're subscribed. Now, if we remove the hypervisor, how do providers maintain security? This is where DPUs come in. NVIDIA Bluefield DPUs run a completely separate Linux operating system on dedicated ARM cores. They handle network virtualization, encryption, and security, physically isolated from the host CPUs. This enables zero-trust architecture. The Kubernetes control plane runs on the DPU, not the host. Hardware crypto provides wire speed encryption. Even if an attacker compromises the host, they can't reach the network layer. It runs on separate hardware. As a bonus, this offloads 3 times the CPU cycles otherwise spent on networking. More cycles for training. You get virtualization-level isolation without the performance penalty. This isn't theoretical. The bare metal advantage has been validated at scale. In MLPerf version 5.0 from June 2025, bare metal infrastructure delivered record results. 2,496 GB200 GPUs trained Llama 3.1 405 billion parameters in just 27 minutes. That's 2 times faster than comparable clusters, and the submission was 34 times larger than other cloud providers. In production, Character AI reports a 13 times cost advantage with bare metal, serving 20,000 queries per second. These results come from combining bare metal with InfiniBand networking, topology-aware scheduling, and proactive health monitoring. The infrastructure is purpose-built for AI, not retrofitted from general-purpose cloud. Let's bring it together. AI training has fundamentally different infrastructure requirements than traditional cloud workloads. Virtualization adds 15 to 25% overhead that compounds over weeks of training. GPUDirect RDMA and NVLink require direct PCIe paths that hypervisors intercept. Kubernetes on bare metal provides automation without sacrificing performance, and DPUs enable zero-trust security without touching your workloads. This is the architecture powering every major LLM training run, from GPT to Llama to Claude. If you found this helpful, subscribe to the channel for more AI infrastructure deep dives. Thanks for watching.